Okay, so today's lecture is the third last lecture. So we have three more lectures. And given that I only have two more lectures that I will lecture because Natalia was very kind to invite a colleague to talk about power to methane, power to gas, which is one topic which I didn't address in this lecture. We will address briefly in this lecture. So this lecture is going to be other energy storage. So it's going to be the technologies that I have not addressed in this lecture. One because I forgot to address, another one because I found out the technology while doing the course. There's a lot of new technologies being created in the market. And I'll also talk a little bit about Brazil, Brazilian energy markets, the Brazilian PLD, and some of my experience on the sector. I guess I might as well show the lecture summary. So liquid metal batteries, solid state lithium ion batteries. Sorry, there's no ion there. It is lithium ion because yes, the lithium ions is the one that goes from the cathode to the anode, but they usually don't put ion when they describe this technology. Ultra capacitors, fossil fuels, power to gas. I'm gonna just mention it briefly. Hourly electricity prices in Brazil, energy storage regulation in Brazil, and some ANEEL, PID, PND, R&D talking about energy storage. Right, so I'm going to talk about liquid metal battery first. So liquid metal batteries, they are usually, well, any battery, they have atoms from one side, which wants to be a positive ions, and the other side, which wants to be negative. You combine them both. Usually you put this in the anode, and these ones are in the cathode. Sometimes lithium, for example, um, so lithium and cobalt. Lithium wants to be by itself on the anode and stays on the cathode with cobalt, for example, manganese, nickel, and several other. So this is a lithium ion battery. But I will talk about liquid metal battery today, and these are the materials used, and I'm going to explain a little bit more in detail. So this is a liquid metal battery. It was created in MIT, which is Massachusetts Institute of Technology, and it consists of several metals, which are mainly calcium and antimonium, which is this SB is antimonium, and it is in a solid state in this image. So several minerals components that you add into this battery, but in order for it to function, you need to melt the minerals. So after you melt, you increase the temperature to 500 degrees Celsius. What happens is that the density of the different minerals that are formed will result in three different layers. These layers will depend on the charge, how much electrons are inside the system before it melted, because it's going to impact the conformation of these alloys. I'm going to explain a little bit more in details. So the ones that are lighter, which is calcium. So calcium is lighter than antimonium. Antimonium is heavier. So antimonium, heavy metal precipitate, is in the bottom. Calcium, which is lighter, is on the top. And you have a molten salt electrolyte, which it has a density between calcium alloy and the antimony. This electrolyte is usually, so in this case, is a combination of chloride, so Cl, chloro, with calcium. It is a mixture of chloride and calcium. And the interesting thing is that in this electrolyte does not dissolve antimony. So it has a very, very small solubility in antimony. So the antimony does not cross this electrolyte barrier. Only the calcium, which dissolves, can cross the electrolyte barrier. So you have a electrolyte which the calcium can cross down or up according to the needs for loading or discharging the battery. So how it works? Well, first you are in the charge state. Your battery is 100% charged. So what happens that you have several your layer, calcium layer on the top is completely charged. The antimonium layer on the bottom has no calcium dissolved, or just a little bit of calcium dissolved. And then when you discharge the battery, what happens is that the calcium in the upper layer gains, sorry, releases an electron. So the electron goes through like a electric system, goes to the other side of this battery. It does not cross the electrolyte also. Why? Because the electrolyte has also a very small current. So it's so for example, ceramic, if you put, for example, in a transmission line, it doesn't allow the current to go through. So it's an insulator. So the electrical insulator, the electrons cannot pass through this electrolyte. The electrons doesn't pass. It's an insulator layer. So then the electron has to go around the circle, the system, in order to discharge the battery. So it generates electricity. You have the electron going to the other side, to the anode side, and then you have this alloy formed, which is calcium antimonium alloy formed. And then after you discharge all the battery, what happens is that all the calcium that you have has passed through the electrolyte, all the electricity discharged. You only have left with the electrolyte and the calcium antimonium alloy. Is there any questions so far? Very interesting battery concept. So this is the completely discharged battery. This is the battery which is charged and you're using electricity, so solar energy, wind power, in order to charge the battery. What happens is charging is that the calcium passes through the bottom to the top layer. And this is described here, charging. What happens charging is that the calcium on the crosses the barrier and then starts filling up the top layer. And how this happens, you charge the battery. So you put electricity in the system, and what happens is that the electrons on the bottom, they leave the system, and then if you put energy power into the system, what happens is that this power extracts the electron from the cathode, which is this calcium antimonium alloy, and then this electron goes through the other way around. So you have to put energy in order to create voltage in order to put the electron the other into the cathode. And then if you create uh, negatively charged part on the top, what happens that the calcium will be attracted to the electrons and it will become calcium back again. You charge the battery again. One very interesting thing, for example, if you have the battery and it's completely charged, so the electrolyte is in the middle. You have the antimony and the calcium, and it's completely charged. And then you have an earthquake, so this battery starts to shake. What happens that the calcium will react very fast with the antimony, and the thing is gonna blow up. Boom. So you have to put the battery in a very stable location. You cannot uh, top it. You cannot turn it around because if you do, it's gonna heat up so quickly that it's going to explode and have a lot of problems. But apart from this problem of having the cathode and the anode mixing by shifting the battery, it's okay. So this battery can only be applied for static systems, for grid storage, for residential storage, and should be particularly big because if somebody doesn't know and you have a small battery and they shake it, it's going to explode. So it has to be fixed on the ground. So another very particular, interesting uh, thing about this technology. So how this battery is usually developed. So you have these cells which are usually like the size of a brick, small cells. Why? Because each one has a small voltage of 2 volts, and you want, for example, the battery to supply electricity at 110 or 200 volts. So you have to put one on the top of the other in order to create a series of batteries in order to increase the voltage of the system. Then you have these batteries, one on the top of the other to add up the voltage, and then you put in a block, and then this block goes into a container so that it can be transported, and it's fixed on the ground in order not to mix the cathode and the anode. Of course, if you stop using the battery, what happens is that the battery is going to solidify, and it solidifies with the 3 different layers, and it doesn't blow up because the density is different. It starts to solidify, and as it solidifies, it becomes solid. So then you can spin it around. You can do whatever you want because the cathode and the anode are not going to react in the solid state. So the discharge energy of each of these um, blocks are something like 3 megawatts hour of discharge capacity, and the efficiency of the system is something around 90%, 90% efficient. So very efficient, several 90 to 80% efficient. So this is the website of the technology that sells the website. Usually, when you sell technology, you usually put try to sell your technology, so you give all the good points of the technology. So they increase a little bit. Is usually 80% efficient. And the funny thing that if you have, for example, this battery storing energy, solar energy during the day and discharging during the night, this 20% energy losses is the energy required for the system to maintain at 500 degrees Celsius. So, for example, you don't need an external heat source in order to maintain the temperature at 500 degrees Celsius, because it's very insulated the system, and you have 20% losses, which turns into heats up the system, and then you can operate the system. So the manufacturer of this technology, they say that the cost is lower, is a stable and modular energy device, is can be quickly implemented. Um, it has a very small fade, so you can use it several times, more than 100,000 cycles. So it's can operate at 10 times more than a normal lithium-ion battery. It does not have an issue if it's overheated, because it has to be overheated. For example, it has a rapid response. So if you turn on the battery, it gives voltage as soon as you turn on the battery, very rapid. It's reliable, it's safe, green, and the materials are abundant. Both materials are abundant in the crust of the earth. And they claim, this Umbri claim, that in the future, eventually, when you have both technologies matured, which is grid storage ion batteries and Umbri, which is the market that Umbri competes, Umbri will be something like 3 times cheaper than lithium ion batteries, because the process is going to be mature. They have a lot of money. People put money, Umbri, and then the price will go down, and they're going to make a lot of money. And we can be happy and generate our own solar power. Just be careful not to turn the battery around, because then it can explode. This is a video. I was going to show a video, but given that we are half an hour already, 20 minutes on the lecture, we might as well I'll just leave here a nice link if you want to learn more about the technology. I'll send you the slides later. And I'm going to talk about another topic, which is solid state lithium battery. So forget about the ion, because usually the name of the technology doesn't have ion, in order to people don't confuse one from the other. But of course, the lithium ions has to travel from anode cathode in any battery, any lithium battery. So this is a lithium ion battery, which is not in solid state. It has an electrolyte solution. Electrolyte solution is a liquid solution, for example, and usually it's alkaline solution. So, for example, uh, QOH, so potassium hydroxide, or another solution that allows ions to travel around, uh, electrons to travel around. So it has to have a very high electricity conductivity rate without resistance, because if not, it heats up and you lose energy in the system. But of course, between the one of the other one, you have also this separator, which doesn't allow the electrons to cross. It has to cross through the energy circle, so the electricity grid, or whichever loads or use of energy you want to use. So, for example, this battery, you have four nodules of the battery, which add up the voltage, and then you have 14 volts. So, three nodes of battery, no, four nodes of battery with 3.6 volts add up to 14.4 volts. But for example, in a solid state battery, the electrode is solid, is not liquid electrode. So for example, it's similar to a fuel cell. Fuel cells, they also have solid electrodes. Solid electrodes are usually a plastic porous material which allows the lithium to pass through. If you have different charge, so you have a charge, a negative charge, lithium ion is positive, it's attracted to the positive charge. Given that the distance are very small and the change in charge is high, the lithium just goes and pass through this electrolyte, solid electrolyte. So that the advantage of having a solid electrolyte is going to be explained in the next slides. So this is a conventional lithium ion battery which has liquid inside, and then you have a solid state lithium battery which the electrolyte is solid, is not liquid, and you also have an all solid state lithium sulfate battery, which the difference with the lithium sulfate battery is that the cathode, sorry, the anode don't only have carbon, but has carbon and sulfur. But I'm not going to address this particular technology because it's a very new technology. This one is um, more convenient, you know, more used nowadays. So this is very new. This is new, but not so new. Which the cathode is literally lithium metal. And this video shows how it works. So lithium metal is the anode, and the cathode is the lithium, cobalt, manganese, whichever uh, cathode that is used in the battery. And I'm going to share a video. But now I learned how to show the video without having you to copy the link and put on your browser.
What are solid-state lithium metal batteries? Let's start by looking at conventional lithium-ion batteries.
Can you hear?
A conventional lithium-ion battery cell
Yes.
consists of three main layers:
Thank you.
a positive electrode or cathode, a negative electrode or anode, a porous polymer separator that keeps the electrodes
Is the
apart,
quality good?
and two electrical contacts, one at each electrode. The electrodes are made of particles of material capable of
For me, the audio is not so good,
the
but
entire cell is
I can
filled with
understand.
liquid that serves as the electrolyte,
Wow.
which is the medium through which lithium ions travel. Let's zoom in to look at what happens inside the cathode electrode particles. Each cathode particle is made up of a lithium-containing metal oxide, such as lithium nickel manganese cobalt oxide, commonly known as NMC. These elements form a stable structure to hold the lithium ions when the battery is in the discharged state. As the battery charges, the lithium leaves the cathode particle and makes its way through the liquid electrolyte, passing through the pores in the separator on its way to the anode. There, the lithium enters the anode particle, commonly made of sheets of carbon, sometimes adding silicon. The sheets of carbon host the lithium until the energy is needed, with 6 carbon atoms holding a single lithium ion. Now let's see how solid-state lithium metal works. In a quantum-scaped solid-state lithium metal battery, there are only two main layers: a cathode, or positive electrode, with an electrical contact, and a solid-state ceramic separator, which replaces the porous polymer separator found in the conventional lithium-ion batteries. Where there used to be an anode, there is now just an electrical contact. The cell is manufactured without an anode. As the battery charges, the lithium leaves the cathode, traveling through the atomic lattice of the non-porous solid-state ceramic separator. Once the lithium is through the separator, it deposits between the separator and the electrical contact, forming an anode of pure metallic lithium. A lithium metal anode allows the energy of the solid-state battery to be stored in a smaller volume, enabling a higher energy density as compared to conventional lithium-ion batteries. Solid-state lithium metal allows for greater range from higher energy density, a 15-minute fast charge, and safer operation by eliminating the organic polymer separator. QuantumScape. The future is solid.
Yeah, so this was the first time I tried to share the screen without you having to copy the link. Um, can you see my screen or no?
I can see, but it's too small. I don't know why.
We'll resume. Yeah, maybe next time I will stop sharing my screen so that maybe before I put the video, then it might work better. Can you see the screen now? I guess so. Right. So why people bother doing solid state lithium batteries? That you don't need all this carbon here. So now what you have is just the cathode and the anode, which is lithium metal, but you don't need the carbon anymore. And how this lithium appears from here, you have a catalyst here, which it's also the electrode, which has negative charge, and these attract the positive ions, and they deposit as a metal lithium in this the top part here. And as the lithium moves through the electrode, it deposits, and then it pushes the electrode, which is negative charge, up. And the main advantage for this battery is that it has a higher energy density. So it's lighter, stores more energy with less weight. And this is very interesting for electric vehicles because batteries are heavy, and you're driving a car, you're also having to carry the battery. So it has to be as light as possible with the highest energy density as possible. So that's why solid state lithium batteries are so important. Um, for example, if you go to Alibaba, so I always give an example for Alibaba, you can buy a solid state lithium ion battery for $370. And for example, the solid state battery would cost something around $854 per kilowatt hour, which is something like 5 to 6 to 7 times more expensive than a commercial lithium ion battery. Given that the difference between both is just the fact that the solid state lithium ion battery doesn't have a cathode. No, it's not the only difference. Also, the difference that it doesn't have electrodes, so it's not immersed in liquid. So also, the lack of liquid reduces the temperature of the system, the weight of the system. I'm sorry, I'm close to my boiler. My boiler is making some noise. I hope it doesn't bother you so much. So in the description, you can see that this battery particularly, that's relatively cheap, has 259 watts hour per kilogram, which is substantially higher than Tesla battery that they use in their car, which is something like 170, 150, depends on the year that the battery was developed. This is similar to, for example, the new batteries from Toyota, which are also solid state lithium ion batteries, which is substantially lighter. And these batteries are for solid state lithium ion battery for long range drones. For example, in China, they sell drones. They love drones. So they drive these drones and you're flying with this device, which is the energy supplied with batteries, and the battery needs to be very light. So that's why they use solid state lithium ion battery drones, flying drones. So the evolution of lithium solid state lithium batteries, you have this is the normal lithium ion battery, which has electrode, which has liquid, and then it evolves to solid state batteries with no water and with the electrodes. So the modules had to be very small in order for the small voltage to pull the lithium ions without requiring the battery to be dissolved in liquid in liquid electrolytes. And then so the first stage was a normal battery with anode and cathode without liquid. And then the next stage is without this carbon. So then the anode becomes just the lithium metal. And then after this, so there are the new batteries. You have sulfur added in the cathode, which increases the voltage between the anode and the cathode. And another one which has an even higher energy density is if you have the cathode as oxygen taken from air, so is a becomes a lithium air solid state battery, which the oxygen from air starts depositing oxygen into these cathodes. The lithium is travels to the anode, generating electricity, and as much as you use the battery, the weight of the battery increases because oxygen deposits in the cathodes, pushing and removing the lithium to go to the other side. But is the lightest, is the best for EVs. Probably in the future we will be driving cars with this lithium air solid state batteries. Right. Any questions about solid state lithium ion batteries? Is anyone hearing me? Is everything okay? Yes. Yes. Because if I don't get any reply, I don't even know if I'm connected. Okay, so ultra capacitors. Now we're going to talk about ultra capacitors. Normal capacitor, which you have in your computer, in devices, for example, electrodomésticos, they have capacitors. You have a positive electrode, a negative electrode, and you have a dielectric area, which can be air, which can be ceramic, which can be any material which is an insulator. And the electricity is only stored within the electrodes, which can be a metal, which can be carbon, graphene or something. And then you have ultracapacitor, which is similar to a capacitor, but in the middle it has an electrolyte, which is usually immersed in liquid or not. So nowadays they're making electrodes without liquid. And these electrodes is usually graphite, because graphite has a very high surface area in order for the electrons to be deposited on the surface of each side of the electrodes. So this configuration of ultracapacitor is completely discharged. So the electrons, the surface of the electrode, it's in equilibrium. So you have as many positive and negative charge. So it's discharged. And then you have a battery, which we explained in another lecture, which is similar. You have electrode, cathode, anode, electrolyte. Yes, so the capacity of the ultracapacitor is equivalent to the area of the electrolyte. The electrolyte might be, for example, graphite with a liquid, which could be uh, phosphate hydroxide, usually alkaline liquid, which allows the electrons to flow inside the electrolytes. Nowadays, have solid electrolytes, which are very small in order to allow the small voltage to push the electrons around. And the total capacity is usually the capacity of this cell and the capacity of this cell in this equation. So it depends on the amount of area in this cell, the amount of area in this cell, which can be the area. So, for example, graphite. Graphite is very porous, kind of a mesh full of holes that the electrons go and fill up these very porous media, which is graphite, like a pencil that you draw. And the other one is also the distance. What I mean about the distance, it is the distance from the graphite in this electrode to the electrolyte. The electrode. Then you multiply both on the top, you divide the sum of them, and then you have the final capacity of the whole system. So this is the charged ultracapacitor. This is discharged ultracapacitors. Thank God I'm teaching mechanical engineers because I'm a chemical engineer, so I'm not 100% knowledgeable about ultracapacitors. But that's, I mean, the most detailed that I can go. If anyone knows better, please let me know, or I should make a comment if I made a mistake or something. So ultracapacitors, they use static electricity. So the difference in charge, positive attracts negative charge. Batteries use chemical reactions. So the benefit of ultracapacitor is that it can be charged very fast. It has very large life cycle. Just if the graphite in the middle is decomposed or the system is rusted or damaged physically, and extreme temperatures. So it also operates well at very high temperatures. So, for example, if you want to store energy in a drilling rod 6,000 meters deep to extract oil, then the temperature, the pressure is very high. For example, ultra capacitors will have good performance in this situation. So extreme temperature situations it's preferable to use ultra capacitors. So comparing ultra capacitors with batteries, these are both in logarithmic scales. You have the ultra capacitors have a huge power density. So in a very small ultra capacitor, you can provide very high power. So for example, in 1 second, you can discharge the whole electricity, less than 1 second. Whole electricity that you can store in the ultra capacitor. However, with a small weight of the battery, you can only store very small amount of energy. So for example, the batteries from Elon Musk are something around 200 watts hour per kilogram with batteries. The ultra capacitor only stores 10 watts per kilogram, 20 watts per kilogram. So something around 10 times smaller storage capacity. However, there are in the future when graphene becomes very cheap. So these ultra capacitors they usually use graphite, uh, graphite. So graphene, which is different to graphite, which instead of being a block very complex, very complicated, with several faults and errors in the structure, you have several layers of graphene perfectly stacked on each other, which allows the electrons to be very well distributed in stored in these graphene layers. Then the energy density of the ultracapacitors will be similar to batteries. And then you have ultracapacitor with very high energy density, similar to batteries, so you can drive a car with ultracapacitors. And then in that this whole energy that you can store in this ultracapacitor, you can discharge in 1 second. So you can give a huge amount of electricity in very tiny amount of time. So maybe in the future we will be driving cars with graphene ultracapacitors. But of course, probably when we get there, we have another technology which stores energy much lighter than graphene, and then graphene is not going to be used because we have other batteries, for example, hydrogen. Hydrogen is extremely light, and other solutions which are lighter than this, but this is the theoretical maximum energy density. This is a picture, an image of an ultracapacitor being charged or discharged, just showing that the electrons is stored around the carbon. So the carbon, uh, each carbon is connected by two other carbons. This carbon needs, for example, another electron. So it has a positive charge. And then this double ligações duplas, né? Become uma ligação única com carbono menos. And then that's the way you store electricity in graphene. So ultracapacitors are interesting, increase the performance. And so what are the applications of ultracapacitors? One application which is now used is increase the performance, longevity, or in charge in minutes. So for example, if you have an ultracapacitors operating with a lithium ion battery, then you have very variable electricity load or charge. What the ultracapacitor does is that it removes this noise, this fluctuation, and provides a very constant flow of charge into the battery or out of the battery, which can increase the lifetime of the lithium ion batteries up to 5 times. Of course, this depends on how the lithium ion battery is used. For example, you have a phone, and then the consumption of electricity varies a lot during the day because you're using it, because you call, you do a lot of things, and then the charge is varying substantially. Then your battery is going to run out in 1 year, 2 years. But for example, if a phone had one of these ultracapacitors, it could last for 4 years. Why? Because lithium ion batteries, the more stable the flux of lithium ions, the less dendrite it forms, the less damage to the battery overall, the less temperature increase, the more efficient the battery is, and then you can increase the lifetime. So I gave a lecture on flywheels, and I mentioned the same thing. Nowadays, if you go to Alibaba and you want to buy um, an inverter with a flywheel, it's available. Why? Because the inverter with flywheel increases the efficiency of the inverter. It's also, if you have a battery in the system, it also increases the lifetime of the battery, as explained. And I'm explaining again because ultracapacitors are good for this, because they have this very good uh, power density, and power costs. Power is very cheap. They can charge and discharge really quickly, so these noises are removed cheaply. So this is an example of different brands for ultracapacitors. Selecton supposedly is the cheapest, um, and the specific energy is 10 watt hour per kilogram, and the energy density per volume is particularly higher in this case. So there are different suppliers, different manufacturers of ultracapacitors that you can see here. And of course, I take an example from Alibaba. As I said, Alibaba is always good because they give all the details of the product and they give the cost. For if you want to buy a product from Europe or products from the US, you need to sign with them an MOU. You need to explain what the project is. You need to make an offer. You need to buy equipment in order for them to tell you the price of the product. But in China, no, they tell you the price and they tell you all the details. It's great. This is ultra capacitor used for cars, particularly those cars that when you park in a traffic light, it turns off to save battery, and then in a very short amount of time, you need um, rapid release of electricity in order to turn the car back on. So they use ultracapacitors for this to give a large charge in a short amount of time to turn on the car again. So for example, the specifications of the battery, you have that the power density, not the energy density. So energy density is from 20 to 10 watt hour kilograms, very low, but the power density is 7,480 watts per kilogram. Usually a battery is around 190 up to 100 watts per kilogram. It's similar to the energy density, the power density of batteries. It's similar to the energy density of batteries. But of course, instead of watts is watt hour because energy is watt hour, power is in watt. Right. Any questions about ultra capacitors? I try to make it as interesting as possible, but I really think that ultra capacitors are not interesting. That's why I put in others and talk 10 minutes about it. Any comments, questions? No questions? So fossil fuels. I only have one slide for fossil fuels because you probably had several lectures in your life. You know everything about fossil fuels, but I'm talking about energy storage. Fossil fuels are very related to energy storage. You have coal, oil, natural gas, for example. And yes, the storage side of fossil fuels, they are stored in the earth crust. So you have reservoirs, coal reservoirs, which you have open mines, deep mines. You have oil extraction, which can be conventional, uh, shale gas, shale oil, which is unconventional, and is also stored as reservoirs. So they have huge reservoirs, which cost some money to reach the reservoir to extract the oil, but it's still stored in the ground. And gas also. And then after you extract the gas, to store it on the ground, you can also store in man-made storage, coal storage piles, oil and gas storage tanks. You can use, for example, salt domes to store the natural gas. So you put back in the earth crust in order to store the gas that you extracted from another location, which you're currently extracting, but you store it in another place. For example, so fossil fuels, yes, you can store. The other interesting aspect is that, for example, coal, oil, and natural gas, they themselves have electricity, no, have energy stored in their molecules. So they are energy carriers. So in order to extract energy from these resources, you need to burn it, you need to pass it through fuel cells. I explained to you previously the hydrogen lecture. For example, you can use fossil fuels to generate electricity with fuel cells, which have much higher efficiency than burning. So yeah, that's fossil fuels. Any questions about fossil fuels? No questions. So power to X. I'm gonna briefly talk about it, but we'll have a lecture about the topic. Petra is a colleague from Natalia. She's gonna give a whole lecture about power to X. So power to X, there are several modes. So power to X is usually, it was named because you have power to gas, power to liquid, power to diesel, power to gasoline, power to ammonia, to transform electricity into energy carriers. And then given that there are so many different energy carriers that you can produce with electricity, nowadays they call power to X. So this slide we show that you can produce methane, you can produce liquid fuels, gasoline, diesel, you can produce ammonia, you can produce all electronic chemical synthesis, so other fuels. And the idea of power to X is becoming so important is because you use renewable energy, so renewable electricity, and most of these systems for power to X you require water also to produce hydrogen, and then with this hydrogen you mix with CO2, carbon monoxide, and then you produce methane. After or you can produce uh, gaseous synthesis. I don't know how to gaseous synthesis, synthetic gas, synthesis gas, something like this. And then with this gaseous synthesis, with the Fischer-Tropsch synthesis, you produce gasoline, butano, etano, metano. You can increase the length of hydrocarbons, whichever hydrocarbon you want to produce. And if you use hydrogen with nitrogen in the Haber-Bosch process, you can produce ammonia. Ammonia is it's much easier to transport than hydrogen. So, for example, if you want to transport hydrogen from Brazil to Europe, you can produce ammonia, and then in Europe they transform ammonia into hydrogen, or they can turn ammonia into electricity, or they can burn ammonia to have heat. There are different arrangements that you can use, and these are all power to X. But comparing, for example, a power to X system with, for example, batteries, so if you use a battery as a comparison, so if you have 15 kilowatts hour of power, you can drive a battery car around 100 kilometers. If you use the same 15 kilowatts hour of power, and you use this power to produce hydrogen, and then you put the hydrogen in your car and you run the car with a fuel cell, then you have 35 kilometers that you can drive with the electricity that you have. I'm sorry about this. And then you have synthetic gas, which is gaseous synthesis. I never heard of a car that runs on gaseous synthesis. But imagine you have a car that runs on gaseous synthesis, then you will have to get hydrogen, and then from the hydrogen you mix the carbon dioxide in a gasification chamber, and then you produce gaseous synthesis gas, and then you put in your car. You have a internal combustion engine, and then you can drive, or you can have a fuel cell. Maybe with fuel cell, maybe this is using a fuel cell, and then you have 20 kilometers that you drive. Another example is if you turn water into hydrogen, hydrogen into this gas, and then synthesis gas into diesel or gasoline, petrol. And then you put in the internal combustion engine, and then you can drive 15 kilometers. So this is the electricity. This is the electricity they generate with uh, solar panels, wind power. This is how much you can drive. Of course, it's much better to use a battery. That's why you have several EVs, battery cars. Doesn't make much sense to produce diesel with electricity. As you can see here, you throw away 85%. But why are people so interested in Power to X? Why am I talking about Power to X then? Because you have final demand, which is fuel for transportation, and then you have car batteries, EVs, which are growing. So you can sell electricity for transport because more and more people are buying battery cars. But then you have hydrogen cars. There are not so many hydrogen cars. There are very few actually uh, hydrogen stations that you can fill up your car with hydrogen. So there is not much hydrogen demand, and you can't start producing fuel stations if you don't even have the hydrogen to fill up the cars. But you have a lot of demand for gas veiculares, GNVs, and you have a lot of diesel and petrol cars. So what you can do is that you can start producing a lot of hydrogen. Some of this hydrogen can be consumed, turned into these fuels, and then you can actually sell. But then you start producing hydrogen. You have Power to X is kind of the first step for a hydrogen-based economy because you produce the hydrogen that will be used to produce diesel. And after you have a very high, large hydrogen industry, then you start increasing the number of fuel stations. Then you start building, selling hydrogen cars. The price of hydrogen cars will go down. So the whole thing of Power to X is to give a kickstart for the hydrogen-based economy and create demand for hydrogen in order for the hydrogen economy eventually become a reality, and then you have hydrogen cars, and then you don't need to do this anymore. The chicken and egg problem. Power to gas, Power to X helps with the chicken and egg problem of hydrogen. In the future, after we have several hydrogen cars, and yeah, we in the future we are very sustainable. We will have power being generated with solar power, with wind power, electricity, which can be used for industry, heating, cars with battery cars. And then we have hydrogen production with the excess electricity that, for example, you want to store energy seasonally, and storing energy seasonally cannot happen with batteries. So you produce hydrogen, you store in salt dams, and then you have to use this hydrogen. Then you have hydrogen cars. Then you have, for example, industry that consumes hydrogen. Then you can burn your hydrogen in heaters. And also you have ships running in hydrogen. Ships, they travel 2,000, 4,000, 10,000 kilometers, and you can use batteries because a battery is only for 20, 50, 100, 300 kilometers range because they're very heavy. And it makes no sense to carry a battery 10,000 kilometers in order to transport goods in ships. So you use hydrogen. Or what you can do, you can turn the hydrogen into fuels, and then you can put this fuel into the shipping container. So when we are living in a sustainable world, we have no production of CO2. So we'll be CO2 free. We have to take the CO2 from the atmosphere, literally, or from biomass processes because biomass is sustainable and produce CO2. But because in order to produce hydrocarbons, we need CO2 because hydrogen doesn't have carbon. So we need to take the carbon from somewhere. So then it comes from the CO2. And then this is interesting for planes, for example. So there are a lot of developments for hydrogen planes already. So this line here should come to hydrogen. This hydrogen should come to planes. But for example, if you're traveling very far, maybe the storage tank and the plane cannot hold because the volume of hydrogen, even in liquid form, is still very large. Then the planes will have to have different designs. But even if you're traveling very far, hydrogen might not be the best solution. It might even make sense to transform hydrogen into fuels in order to fly planes in the future from one side of the world to the other side, very far destinations. And the other industry, the other service that's very important is the petrochemical industry. I already made this question to you, but I'll ask again, why you can't use hydrogen in the petrochemical industry? Can anyone answer this question? I'm not sure if you remember, but I asked this question in the past. Anyone? No one wants to answer. So the answer is because petrochemicals have carbon. For example, polymer or whatever you produce in a petrochemical, it has carbon, and hydrogen doesn't have carbon. So you need carbon. So you have to take the carbon from CO2, turn it into fuel to have carbon to produce plastics, to produce lubricants, to produce paints, textiles, and other material products, petrochemical products. Okay, so another video. Let's see if it works now. They're gonna talk about Power to X, but of course they're much more knowledgeable than I am,
For
and much more interesting. I'm not sure. Please let me know if you can. Let me stop sharing this now. Oops. Let me stop sharing before. So I'll stop sharing. Let's see if it improves now. Now, so if you want to share your video in Google Chrome while you're giving a lecture or giving a presentation in Google Meets, you can do it, and I'll teach you how to do it now. Very happy to find this out. Delete this because we already saw this video. You come here. So your lecture has to be in your Google Calendar, and it has to be running, and the link for your lecture has to be the link for the Google Meet link that we all in the same link. So you have to have an event in Google in order to make this happen. And then you come to Google Chrome. I'm not sharing my screen. I'm gonna share my screen so that you can learn. Very useful skill. Very useful. I'm sharing my screen again. Perfect. Then you come here, 3 dots. You put cast, and then this window will appear. You click the right button, and then you allow this show icon, so then it's always here, and then you put optimize full screen video, and this will show up. So then what you do, so you stop your presentation so that it runs smoothly. You click in the video that you want, in the tab that you want to show the video. Of course, I'm not sharing my screen anymore, but then you click in that new icon that appeared. You appear Aula Armazenamento Energético Promec, and you click in the Aula Armazenamento Energético Promec, and then you run the video.
For an all-electric society to become a reality, a lasting solution is needed that addresses the storage and transport of energy generated will still be needed as well.
So when in the middle of the video, I stopped recording and then the quality improves. So my computer processor doesn't manage to do the both tasks at the same time. So next time I'll stop recording when I show the video also. And let's go back to the lecture. I pressed the wrong button. I am presenting. Can you guys see my presenting screen? I guess you can. So I'll go back to the slides. Now you know everything about power to X. Let's move on. Any questions? No, sorry, I have more slides for power to X. So power to X cost distribution. Very interesting to know how much it costs. So 31% of power to X is renewable energies. Renewable energies are expensive, but it takes only 31% of the costs. Then you have the electrolysis system to produce hydrogen, all other 31. This is to produce methane. So methane is natural gas, which is not natural because it's artificially made, so it can be called natural gas. It's not extracted from the ground, it's methane. So it's not natural, it's artificial methane. Then you have hydrogen storage. You produce the hydrogen, you want to store it because you want to produce the hydrogen when you have renewable energy, cheap renewable energy available. Then you have 15% of CO2, which can be either carbon capture and storage.
Julian,
Hello.
I think you're not sharing your screen.
Thank you so much. Thank you, August, so much. Yeah, because this is interesting, very interesting slide. So methane, not natural gas. Power to methane. So methane, 31% of the system of the whole cost for producing methane from power is 31% is the power, 31% is the production of hydrogen. You can see if you want to produce hydrogen, half of the cost is for renewable energy and the other half is to produce hydrogen. And then 2% is for storing the hydrogen because you want to produce hydrogen when you have power available. So we store, it's essentially cheaper to store the hydrogen. And then you have the CO2, so you have to produce CO2, which can be separated from nitrogen, nitrogen oxides, other flue gases from burning fossil fuels or biomass, which is the carbon capture and use. Or you can extract from the atmosphere by absorbing with different systems and removing CO2 directly from the atmosphere. This is probably the energy cost for removing CO2 from the atmosphere because it's very expensive here. And then you have the production of methane from hydrogen, which is done with a methanization process, which will combine hydrogen with CO2. And with this combination, you produce methane and water. You have to have catalysts. It's a very detailed process. I'm not going to go very much in detail here. And then you transport the methane. Very expensive methane transport. Maybe you transport it into another country, another continent. This is a lot of energy. For example, you produce methane in Brazil, you send to Europe. So 80% will be the cost for transporting the methane. You have to liquefy the methane and all the other costs that are involved. So the other process is power to liquid. So gasoline, diesel, of course, the longer the hydrocarbon chain, the more energy it's required, the higher the cost also. But so this process, you have 31% for power generation, 31% for hydrogen production, so the same as the previous one. Uh, Hydrogen storage also the same cost, but then you need more carbon. In the large hydrocarbons, you have more ligações carbono-carbono. You need more carbon, and these ligações carbono-carbono increase the rate of CO2 costs. But then also you need a higher cost for actually producing these long hydrocarbon chains, but the cost reduces. Why the cost reduces? Because it's liquid. You don't need to liquefy methane. So overall, if you want to sell methane to Europe, if you want to produce methane in Brazil and sell to Europe, or you want to produce diesel in Brazil with power and sell to Europe, is the same cost. Why? Because it reduces the cost of transportation. Great. It's expected by several sources, several references, several scenario producers, academics, companies. Reports show that the cost for power to X is going to reduce something like 5 times up to 2050. I'm going to share this presentation with you. You can read more if you're interested. And you have several projects in Europe. I say several projects in Western Europe. You have one project in Eastern Europe, which are demonstration projects for power to X. And you have several projects in Europe, in Germany. Germany. Every publication about power to X is in German. Is a German company. Germany loves power to X. So why Germany loves power to X? Because Germany doesn't have mountains. Germany doesn't have fossil fuels. Germany needs energy storage solution, but it doesn't have mountains for pump storage, long-term energy storage solution, seasonal energy storage solution. And for some reason, Germany loves these power to X. And you can see they have power to hydrogen, power to methane. So in 2014, they produced more methane with power than hydrogen. Then in 2018, they had more hydrogen being produced, and they increased their production for methane. And then 2021 until 2021, the plants that are in construction and planning, they will be producing also hydrogen. Some of them will be cancelled, and they have power to liquids. They're gonna start producing liquids, and there are several work showing the increase of gigawatts of electricity power used for the production of X, which is methane, hydrogen, liquids. Up to 2050 is going to reach up to 350 gigawatts. So Brazil power generation capacity is around 160 gigawatts. So Germany by 2050 plans to spend 2 times the electricity generation capacity of Brazil to produce X, so hydrogen liquids. So they're going to invest a lot of money in the next 10, 20, 30 years to produce hydrogen and gases and liquids. Right, it's finished. Any questions about power to X? If you know how to speak German, you can read several references about the topic. I personally don't know how to speak German. even though I lived in Austria for 3 years. Anyone? No questions. Perfect. So talk about hourly electricity prices in Brazil. We have 40 minutes. So electricity costs in Brazil have changed from weekly variations. So every week they had a cost for electricity because they ran the comp. First they run new wave, the results from new wave go into the comp. The comp, you run the comp, and then every week ONS runs the comp Friday, every Friday for next week, which starts on Sunday. So then Friday they know the cost of electricity of next week. Then if you were last year in the Mercado Livre, Friday you would know the cost of electricity of next week, depending on the rain, depending on the temperature, the demand of heating, several reasons. Sometimes power plants have to go into maintenance and they have to shut down, for example, Angra 1, Angra 2 to change the fuel rods. Several reasons that could affect the price of electricity in Brazil. They put all this information in these two software, New Wave, the comp, and then they gave you the weekly cost of electricity with the comp. That happened from 2003 up to 2020, and in the last day of 2020, the first day of 2021, the cost of electricity changed to hourly electricity. So after they run this decomp, which gives the cost of electricity per week, you have to run the Descent, which is another software, which takes into account the demand per each barramento, which is each substation, which distributes the electricity, takes into account the limits in transmission for each barramento in more details. It looks into the rampas, the ramps, so the amount, the capacity of thermoelectric power plants, hydroelectric power plants to increase generation. It takes into account wind power, solar power, several other renewable energy technologies which are not dispatchable. And then they put all the information in the model. The model has all the power plants in Brazil. Usually for wind power and solar power and these things, they don't have every power plant, but they have an overall generation per region. You also have the restrictions for water flow that varies because sometimes it rains a lot, sometimes it doesn't rain so much, and then these restrictions for flow, natural flow, also change. And then you put all the information in the model, it gives a price of electricity. It's not actually an hourly electricity price. They give 30 minutes electricity price. So there are 48 different prices per day. 48 is 24 times 2. So every 30 minutes, they have a price of electricity. So this is the hourly electricity price of Brazil from 2018 2020. It was just before it changed it actually become a reality, this hourly electricity price. So this price here is now, of course, up to date. You have 2 more months, so January and February 2021, but the curve doesn't change so much. The cost now is something around 150. The average cost of the weekly average cost of electricity is 150. So the cost from the same, so 150 somewhere around this level because it rained substantially. So it stayed until 300 somewhere around the end of January, and then went down to 150. Right. So it doesn't vary weekly anymore. It vary hourly. So this was the design that they used since 2018 because they were improving, changing the model. As you can see here, behaved very differently to here. So 2019, it behaves very differently to today. And because they are improving the model, they are trying to, make the model actually lower the cost of electricity, improve the operation of the system, reduce the costs and emissions, whatever they're interested to impact the system. And now they're the same. Every week they change. Sometimes they want to make some extra money, change. They sell a lot of electricity, they change, and then the price go down, and then they buy a lot of electricity, the price goes down, then they sell, they make a lot of money. ONS, now they're changing the rules all the time, which makes no sense. But they do this all the time. They make a lot of money with the fact that they know, of course, what they're gonna change, how it's gonna impact the costs. That's how it happens. So this is the main regulation of Brazil, which is these three software, which dictate the cost of electricity in the country. In Europe, in the US, for example, who dictates the electricity in the country is the market. So, for example, a company believes that in 3, 4, 5 years, the cost of electricity will be X, and they'll buy or sell electricity in the future, and they decide what's the cost. The companies, the people that buy, the people that sell electricity, dictate the price. It's not a software. It's businesses and companies. It makes much more sense. This is completely centrally controlled by ONS, ANEEL, and the Ministério de Minas e Energia, free software. That's the cost of electricity in Brazil. Right. So I had this data. I tried to make some analysis of the cost of PLD. So the distribution of PLD horário vary from, for example, from all the years that we have since 2018 to 2020, we had 3,000 hours where the cost of electricity was between 50 to 100. 3,050 hours where the cost was between 150. So this is the distribution of electricity prices per hour in these periods. You have that the cost was somewhere around 50 to 350 reals per megawatt hour. And there are a lot of costs around here because it's the peak nowadays, because the peak in 2014 was 150. But then they lowered the upper limits of the PLD. Now it's around 150, now 550. So any value above 550, the PLD is fixed at 550. And also there is a lower limit, which is 40. Not sure why I didn't put the 41. So there is another column here which shows from 0 to 40, and if it goes below 0, for example 10, 0, it can go even minus 20. For example, you have too much generation and not enough demand, the price can go down, but the price of the CMO, which is the custo marginal de operação, not the PLD, because the PLD's minimum value is fixed at 40 reais per megawatt hour. So the distribuição média diária de PLD horário, so the average daily. So here we're not talking about hours, we talk about days. We have that the most frequent PLD average, daily average, was from 100 to 150. Also here 500 to 550 is high, and it changes a little bit. You see, like in the PLD horário, you have a higher value with higher costs than the daily average. So the daily average, you have the cost go down. So what happened now is that the PLD is horário, you have a higher cost of electricity. So cost of electricity from one year to another increase, let's say 20% in the Mercado Livre, of course, just because you're running the same now. Because you can see the difference, right? Between one graph and the other. So the cost of electricity is higher because we're running horário, and the DECEM, because the DECEM add new restrictions. These new restrictions imply a higher cost of electricity, particularly during the peak hours. So from 6 o'clock to 9 o'clock at night, sometimes when it's very hot and everyone goes back home and the house is very hot and they need to heat up the whole house. It's like an inferno. It's really, really hot. Then turn on the air conditioning, and then the demand goes very high. It's a peak demand. The costs go up also, and then the cost of electricity overall in the whole country increase because of the change to período horário. So taking the same data and looking at the average, you have the average electricity, for example, the lowest average cost of electricity at 3 o'clock at night is around 227 reals per megawatt hour. And the highest cost is at 7 o'clock, around 262 reals per megawatt hour. But if you compare 226 to 227 to 262, the difference is only 10 to 20%, 10 to 15%. So the cost of electricity during the day in average only varies 10 to 15%, which is not so much. I'm going to talk about it in more details. If you take the percentiles, so the 15 percentiles, 15% of the, no, 25% of the time in the lower section, you have the cost, the daily cost of electricity behaving like this. 75% of the percentile, that you have the cost of electricity going like this. So the variation increases more because usually the cost of electricity is higher. So the peak is closer to the peak that the capacity of the whole country can supply. So then the peak cost becomes even higher. Then you have a higher change difference in the hourly electricity generated. And then you have the average. In the average, also the change between the night and the peak hour is very small. And another very interesting graph that you can see is that if you're comparing per each average daily PLD, so you have the average daily PLD. So if the average daily PLD is around, let's say 450, the average variation between the lowest and the highest cost is $15 per megawatt hour. If the cost is lower, let's say 100, the average cost difference between the high and the low is 5%. For some reason here in the middle, you have a big jump, probably because it's a section where the cost between one power plant that is activated and the other one, you have a big jump. You have 50 to 40 reals difference between the CVU from one plant, and then you increase the demand, you have to turn on another plant, and then this other plant dictate the price. The difference between this power plant and this power plant is 50, 40, which is a high difference. Then you have a jump here, of course, because the average cost is relatively smaller than here. So then you have this big peak. But well, the interest of this graph is to show that the difference between the night and the day is 50 reals per megawatt hour. So the 3 o'clock at night and 7 o'clock, 3 o'clock in the morning 7 o'clock at night, peak hour and lowest demand is 15. 15 reals per megawatt hour is around $3-4 per megawatt hour, which is very low. So the variation is very low. So it does not make any sense to invest in batteries or any storage technology. So this graph shows that energy storage in Brazil makes no sense in the grid scale, the Mercado Livre. So if you want to make money with batteries in the Mercado Livre, you're going to falir in 2 meses, mês. You're going to invest a lot of money, you're not going to make any money, and you're going to go bankrupt. So it makes no sense to invest in batteries. In the Mercado Livre, of course, it makes a lot of sense if you put in the hospital, in a supermarket, that when the peak demand is very high. So during peak demand, the cost of the tarifa de energia is very high. You store outside of the peak time and you use during peak time, like the diesel generators, where I'll talk about it several times. This makes sense. But in order to store energy at night with the cost of the LED and then selling during the night, during the peak time, then it doesn't make sense because the change in cost is very small. On the other hand, for example, we're living in Rio Grande do Sul, is close to Argentina, so I thought looking at the Argentina market would be interesting. Argentina doesn't have so much hydropower, which you can just turn a button and then you automatically generate a lot of electricity, which is the reason why the cost of electricity doesn't vary so much in Brazil. We have around 120 megawatts, sorry, gigawatts of installed capacity of hydropower that is extremely flexible. In 20 seconds, some power plants, you can reach full generation capacity. Is extremely flexible. Is one of the most flexible generation alternatives in the world. Hydropower, like natural gas, but natural gas takes 1 or 2 hours to reach the maximum generation capacity. Hydropower takes 20 seconds to 1 minute, 2 minutes to reach the maximum generation capacity. In Argentina, they only have 20 to 30, 40% of hydropower generation, depending on how much rain they have. And this is the cost of electricity variation from July 2000 to November 2000. And creating the same graph that I created for Brazil, you have when the cost of electricity is around 20, let's say $20 per megawatt hour. Makes no sense to use pesos because pesos is varying like crazy. In this period, maybe the cost of pesos vary 30%, 40%. So much better to use dollars because then it doesn't vary so much with the cambio. And then you have $20 per megawatt hour. The variation between the night and the day is around $30 per megawatt hour. So, for example, the cost during the night is $10 per megawatt hour, and during the night peak hour is $40 per megawatt hour, and then you have an average of $20 per megawatt hour, and the variation is $30 per megawatt hour. And of course, this makes a lot of sense. Probably should make sense in Brazil, but not much things make sense. This is a straight line, so the higher the average cost of electricity, the higher the difference between the night and the minimum and the maximum. It doesn't really happen in Brazil, but it happens in Argentina. And for example, if the cost of electricity is 100, the average cost of electricity is $100 per megawatt hour, the variation during the day is 120. So let's say at night, the minimum cost is 80, and during the peak hours is 80 times 120, which is $200 per megawatt hour. You have an average of 100, and the difference between the mix minimum and maximum of 120. Now we're talking about not only 10% variation, we're talking about 100% variation during minimum and maximum, more than 100. This is the average of electricity variation. So at night, it's something around 40, and during peak hours, is 55. So from 40 to 55 is around 20% difference. 20% in difference in cost. Sometimes you reach 30, sometimes it's 100. So this is just the average. It reaches 100 because, for example, the capacity starts to becoming not capable of meeting the demand. So the price reaches very high. People turn off their industry. The demand has to reduce because the cost of electricity is very high. They turn on very expensive diesel generators in the country. So that's why the cost goes very high in order to pay for the diesel, for the expensive generation solutions. But for example, if you have a battery and you want to invest a battery, the average money that you will make is storing energy at 40, selling at 55, which is around $15 per megawatt hour. In Brazil is $3 per megawatt hour. Argentina is 15. So in Argentina, makes 3 times more sense to invest in batteries than Brazil. But 15 US dollars per megawatt hour is still not it still doesn't make sense to invest in batteries. It makes more sense to invest in a new gas power plant, and then you turn on the new gas power plant during peak hour. It still makes more sense to do this than to store the energy at night to generate during the peak hours. So that's why you don't have so many batteries in Argentina. So hourly electricity prices in Brazil. You have that Brazil has more than 100 gigawatts of hydropower generation capacity, is around 120 gigawatts. This that can be dispatched when required. You just press a button, increase the generation. This contributes to small variation in hourly PLD. This only became a problem, for example, in 2014, 2015, when you had all the hydropower plant capacity, but you didn't have water. So you didn't have water to generate electricity. If you generate all electricity with water, you have no water, period. But of course, they turn on the thermoelectric plants and stuff to save the water in order to generate electricity at least during the peak times and provide the base load with the thermoelectric power plants. But that was an exception. Usually Brazil rains more than 2014, 2015, and the PLD cost prices doesn't vary so much. So the hourly PLD cost was introduced in 2021, this year. The introduction will result in low cost changes in Brazilian generation sectors. So, for example, if you have a power plant and it doesn't cost very much to make a change, that you can generate more electricity during, let's say, 3, 4 hours during peak hours, you make the investment. Why? Because you're gonna have a return in your investment that you will make more profit, you make more money with your power plants. And then the other thing, the main impact will be in the electricity consumption. So if you have a factory consuming electricity from the free market, the Mercado Livre, you, for example, have to pay 20-30% more electricity during this peak time now. In the past, you didn't because the price was the same during the whole week. Now the price varies every 30 minutes. During those particular times, if you really need to reduce your electricity bill, you make some adjustments in your process, and then you reduce the electricity consumption, the cost of electricity of your process, and you reduce the electricity consumption during those particular 3 hours. And then what this is going to result is that this PLD that now is implemented after 100 years of electricity in Brazil, we have a regulation that varies hourly, which for Brazil was probably the last country, maybe the last country that changed to hourly electricity generation. Now, every industry, every residential, every commercial sector, not residential because the consumption is very low and it's not in the free electricity markets. But every customer in the free electricity market can make adjustments in order to consume less electricity during peak time. And then this variation during night and peak hours is going to reduce even more in the next 2 or 3 or 4 or 5 years, because now they're going to have a benefit for consuming less electricity during peak hours. So this is going to have a huge impact on the PLD, mainly the demand side. And then you have the introduction of solar power in Brazil will reduce the PLD during the afternoon, because solar power is becoming cheaper and cheaper. For example, in 2020, there was 5 gigawatts of capacity being imported to Brazil of power of solar power, and the solar power will be generated during the afternoon. So this afternoon price is going to come down because the demand for electricity, the supply of electricity, solar power in the afternoon will increase, so the cost will come down. So the whole PLD curve that I showed you in Brazil is going to change. Let's have a look. So this is probably going to come down like this, and is going to have a peak during 6 to 9 o'clock at night, because you have no sun and the demand is still high. So this curve is going to kind of move like, is going to change like this, which will make, for example, the electricity during these hours lower, and you have a larger peak electricity change during the peak hour from 6 o'clock to 9 o'clock at night. So this curve is going to change because of solar energy also. The PLD horário is going to change in Brazil. It might take 10 to 20 years for daily energy storage solutions to become viable using the PLD as a source of revenue. Why? Because the cost at night to the daytime is very small. The only factor, in my opinion, that could make battery storage viable by using the PLD battery or whichever energy storage solution for daily energy storage is, for example, if solar power increases a lot and the solar power is so high that the cost of electricity during the day is very low, and then it will make sense to store energy during the day and generate electricity during the peak hour at night, or doing even the madrugada, the night. Because also batteries are lowering the price. Like, for example, in the last 5 years, the cost reduced 10 times of lithium-ion batteries. So it could reduce even more, and then it's going to become a viable alternative batteries for energy storage. So I have 10 minutes. Any questions about hourly electricity prices in Brazil? One thing I talk about daily energy storage because you have seasonal energy storage. Seasonal energy storage, the CMO, it varies somewhere around $50 in the período úmido to the período seco, 50. In the daily energy storage, it only varies 15. Seasonal varies 70, 80, 100 sometimes reals per megawatt hour. This 100 reals per megawatt hour change between the two seasons would make sense to invest in a solution for seasonal energy storage, like the seasonal pumped storage solution, which I have published like 5 papers on the subject, and I'm working on a PhD project with CPFL, and I always repeat. If we build now a seasonal pump storage plant in Brazil, whoever build this will become a millionaire. But the only problem, billionaire. The only problem is that we don't have a regulation to pay somebody that stores energy from the período úmido to the período seco. So nowadays, if they invest, They're not gonna make any money because there is no regulation to pay for energy storage in Brazil. So about no one has questions about hourly PLD, so I'm going to talk about energy storage regulations in Brazil. The situation today is that you have, for example, auxiliary services for frequency, voltage balancing, which are already in place. Usually, for example, the Brazilian energy matrix, they use the hydropower plants with the highest head, for example, Barra Grande in the Rio Uruguay, because they can vary the power generation very rapidly. The higher the heads, the higher the response time of the generation, hydropower generation, and they have some turbines generating spinning without actually supplying electricity to the market. For example, if a thermoelectric power plants blow up, or you have a transmission line that is deactivated because of uh, storms or thunderstorms, what happens that this power plant, for example, the hydroelectric power plant of Barra Grande, generates at 100% capacity, but 10% of the generation capacity is not inserted into the power grid because it's waiting for some problem to happen to supply electricity and maintain the frequency of the grid. But so this has a cost. It's throwing away 10% of the generation capacity just to make sure that if you have a problem, it's not going to result in a blackout. If you have, for example, energy storage solution, if you are filling up the energy storage solution, you can instantaneously stop filling it up instead of uh, having to waste electricity that could be generated. You can just stop storing. When you stop storing, you also reduce the demand and you maintain the frequency of the grid in balance. So this is there is a huge advantage on having energy storage technologies in the grid, because when you are storing mode, you can stop storing and then balance the frequency, the voltage of the grid by stop storing instead of wasting electricity that could be generated. So, so this energy storage technology in Brazil could make a lot of money with auxiliary services. But as Bernam explained in his lecture on Monday, energy storage technology is not paid only with one service. It needs 5, 6, 7, 8, 20 services to make actually energy storage technology viable, because it's very difficult to make energy storage viable, because you have several energy generation technologies that are competitive, cheap, that you can use instead of paying a solution that doesn't generate electricity, just stores, and is expensive also. So right, the second point is in 2017, Ministério de Minas e Energia introduced a public consultation to consider separating Lastro e Energia. Well, we have 4 minutes, so I don't have much time. I guess I'm gonna talk about energy storage regulation in Brazil in the next lecture. I particularly find it interesting, useful, because if there is no regulation, all these lectures, 20 lectures, makes no sense, because we won't be able to actually implement energy storage. And I don't have time to finish, so I'm gonna leave for the last lecture, which is the 22nd, because the 21st is gonna be taught by Petra. Petra is Natalia's colleague. Right, guys, thank you so much for staying until the end. I hope it didn't bother you so much.
Thank you, Julio. It was very nice.
Thank you. And yes, if you have any questions about the final reports, just send me email, send me a WhatsApp, or call me. And yes, I'll answer your questions. Good luck on your final submission. Oh, Buffon has a question.
No, so far, no questions.
No questions.
Just learning. Yeah, just more about curious about the PLD. Is already running in Brazil, but how is going that it's already function? The PLD, hourly PLD.
Yes. Um, however, in the companies, for example, uh, electric energy companies, distribution companies that have to buy and sell electricity energy in the free market, comercialização de energia, they still use the average cost of electricity. So they still sell electricity in the monthly basis as it was in the past. So the decomp varied every week, but the comercializadoras didn't sell electricity in the first week, in the second week, in the third week. So the PLD varied every week, but they used to sell, and they still sell and buy electricity per month.
Okay, because the contracts probably the contracts is still monthly.
Maybe,
Something
yeah,
like that.
yeah, it's true actually. Well, probably because first no one wants to bother thinking about finding, I mean, running the same. No one cares about the same, and the same is complicated, makes life difficult, and no one wants to do this. If you want to commercialize electricity hourly, you would have to put a lot of people to learn how the hourly market works, and uh, and the other company that's buying and the other one that's selling, both of them want to do the same thing. No one does. I personally haven't heard anyone buying and selling electricity hourly yet. I never heard about it. Um,
It's okay.
the-
I thought so because
but you had a very interesting approach. Maybe even if you want to commercialize electricity, what happens is that you have to send your contract to CCEE. So if you want to buy and sell electricity, it has to be in the cadastro of the CCEE. If you're doing without the cadastro in CCEE, you can do it, but you should not mention to anyone because it's illegal. So if you want to commercialize electricity, CCEE needs to know that, oh, this company bought, this company sells. They don't even need to generate or consume the electricity. It can be a speculation. You can buy and sell. So who controls the cost is ONS ANEEL running the company wave. It has to be cadastrado no ANEEL. I don't know if actually comercializar LD horário. I don't know. Maybe you can't. Maybe CCEE still doesn't develop the required processes to put in a power in a planilha.
yeah, probably like the
Yeah,
legal issues for doing that and for the contract, something like that.
yeah. No, in Brazil and the companhias públicas, né? The they might say, "Oh, we are working on the platform to allow the commerce hourly daily digitalization." And I don't think from one day to another they have everything ready to allow commercialization for hourly. And I personally never heard. I particularly follow this sector. I have a lot of knowledge on electricity commercialization. I worked on this before, and I know how to run New Wave. I know how to run the comp. I have license installed on my PC. If I want to run, if you want me to teach you how to run the company wave, it's not nice, it's not fun, it's very boring, pain in the ass. But I could talk to you about it. I could have given a lecture on it. Uh, I had a course. It costed 20,000 reals to join the course for consultancy company called.
No, thank you. I'm
Ampere.
good with the message so far.
Okay. Yeah. Anyway, PLD, yes, it's very interesting. There is a lot of money. The market runs something like 4 to 5, maybe even $10 billion. So 2018 was 5 billion dollars. Mercado Livre is increasing very steeply the amount of people buying and selling electricity in the Mercado Livre, and it's 100. Maybe in 5-10 years, it's going to reach $100 billion industry, and every company has maybe every power company have 5 to 30 people working on the comercialização de energia. And for example, I used to work in JBS, Amber, for comercialização de energia, and de comercializadores de energia, vou falar em português, eles ganhavam na JBS. JBS é aquele açougue, né? Cheio de sangue para todo lado, uma loucura. Eles tinham motivação de fazer uma comercialização muito boa, né? E eles são os diretores, lógico, eles querem ganhar um bônus muito grande, né? Querem ficar milionário em um ano. Eles ganhavam 10% do lucro que eles tinham. Lógico que se eles tinham um prejuízo na comercialização, eles não precisavam pagar nada. Eles compravam e vendiam mais ou menos 30, 50 milhões de reais. Então, no final do ano, ele ganhava 5 milhões de reais. Meu diretor lá, pá, quase parecido com o Neymar. O cara nem sabia, nem entende nada de setor energético. Nada de setor energético. Compra e vende energia, ganha 5 milhões de reais.
Nossa,
É muita grana.
muita.
Então, se quer ficar rico, né? Esse é o objetivo de vida. Eu que rodava os modelos, ganhava um salarinho lá, e nem aumentava, né? Eu que falava para ele comprar, ele ganhava os 5 Porra.
Ai, que
Acho que
figura.
eu tenho que largar, né? Largo, deixa de ser professor, vou trabalhar lá na Amber, lá, diretor, chego lá, viro trader, aí volto pra carreira de professor.
Exato, isso aí, ganha uns milhões lá e volta.
O Bufão tá com a mão levantada. Bufão, tem uma pergunta? Ou só levantou há muito tempo atrás que não vê? Não. Ah, tirou a mão. Então, beleza, pessoal. Se tiver alguma dúvida aí, quiser falar sobre algum assunto, pode perguntar. Senão, a gente se encontra aí na última aula, que vai ser semana que vem. Valeu aí.
Tá ótimo, valeu, Julião. Tchau, tchau.
Falou.
Valeu, um abraço.
Valeu, Julião. Tchau, tchau.
Valeu. Açougue, né? Exatamente. Sangue pra todo lado. É um açougue. Um ano, né? Rende o quê? 50 milhões? Os caras ganham 5 milhões já.